Hello, everyone. Welcome back to our YouTube channel, Becoming a ROS Developer here at The Construct. My name is Rodrigo, and today we have one of our students, Adam, who has completed the course ROS 2 Basics in 5 days. And at the end of this course, in order to get one of our certificates, you can present the project that we offer on a real robot. So that's what we're going to be seeing here today. Hello, Adam. How are you?
I'm fine. How are you, Rat? And
I am
thank you.
I am
Thank
very
you.
well, thank you. Very excited to see your project. So please, whenever you can, start sharing your screen to show us how you've solved this project.
Okay. Okay. So one thing before starting,
Great.
it's ROS one in Python.
I'm sorry, ROS 1 in
Yeah.
Python. I misspoke.
Yeah.
Yes.
Okay. So I will start sharing my. Okay. Yeah. Share.
All right,
So
we can see your screen.
yeah. So now I will launch the main launch. Okay. So let's begin.
Mm-hmm.
Yeah. So the first thing, the surface has been called so that the robot can find a nearby wall
Mm-hmm.
and then finding a direction for moving forward. So it should, yeah, now it detected the wall.
Yeah. Oh, yeah, we
And
see that on the
yeah,
Turtlebot.
it moves towards the wall. Then it finds the right direction for moving forward.
Mm-hmm.
Yeah. So now yeah, the wall is found and it starts recording the coordinates from the odometry center, from the
Uh-huh.
action, and it moves forward, of course. Yeah.
Awesome.
Yeah, so it moves, it corrects itself because the robot should be between zero point 0.2 and 0.3 meter from the nearby wall.
Uh-huh.
Yeah, so it moves and corrects itself. It moves. Yeah,
Awesome. And let me ask you real quick.
yeah.
Will this do one lap and then stop, or just do an infinite amount, or how do you
No,
determine when this stops?
it will do one loop and
Uh-huh.
then it will stop.
Oh, okay, okay.
Oh, yeah, and even if it misses the starting point, there is a condition that makes it stop. So I'm enforcing it to stop.
Oh, nice, nice.
So now it moves.
It's very smooth movement. That's a very nice.
Yeah, in fact, I have been working a lot on this part.
Oh yeah, yeah. I can tell. You can see how it's correcting itself very
Yeah.
smoothly. Yeah.
Yeah. So now it finished and
Uh-huh.
yeah.
And we can see the distance traveled.
Yeah, of course, this is the distance traveled here. You can see it. It's 5.4 meter.
Mm-hmm.
And this is a list for the points that it came across.
Okay, okay. So that's the
Yeah.
that's the trajectory it took.
Yeah. Yeah. So X coordinate, Y coordinate, and this is the orientation of Z. So yeah.
Awesome. This is great, Adam. So we tested the demo on the first try and it went perfectly. So could you just explain a little bit how you've done each part of these of this project?
Okay. So now I will come to the code itself.
Oh, okay, yeah.
Yeah. So it So what I have three scripts in Python. Um, a main script for following the wall, and script for service server, and a script for the action server. So the main script is simply a class that has many methods, as you can see. Yeah.
Mm-hmm.
So I will come to these methods one by one. But firstly, let me explain the idea behind. Yeah. So yeah. Okay, so the flow charts of these scripts. So
Sorry, Adam. I cannot see that specific screen. Maybe you only shared uh, the
okay,
the constructs window.
here, okay. Okay, share.
Yeah, now I can see main script.
I'm really sorry. Okay. So this is the main script. So the main script, when it starts, it initializes a subscriber and a publisher. So the first thing it does, it calls the service for finding the nearby wall and then turning for detecting the wall and then finding the right direction. And then it will start moving forward. It will start moving forward, wall follow, and at the same time, it would record the coordinates that it came across. And it also checks whether the starting point is reached after 3 meters, because it's not logical to start checking the point the moment you start, because if you do that, it means that the robot will not move. So after 3 meters, the robot will start checking whether we have reached the starting point or not. If it is reached, then it returns list of odometry, sensor readings, and the distance traveled, and will stop the robot. So this is the main script. I will get back to the code now. Yeah, I think I have to share it again. I'm really sorry for that.
No, don't worry. Don't worry. Got time.
So, okay. Yeah. Yeah, so the first thing is a constructor where I define the parameters. So you can see here, these all the parameters I used in the coming methods. The first method is laser callback. This is for getting the readings from the laser sensor. The second one is the turn method, so that when the robot comes nearby a corner, it turns. And this is a proportional derivative controller, so that the robot can correct itself. In fact, I wanted to use a BID controller, but when I tested the BID controller, the result, I would say, were not so smooth. So the best combination I found is using a proportional derivative controller. So I will come to explain more about it. And okay, I have something to share also. Wait. Share the presentation. Yeah. So, okay. So this BD controller, how it functions. So let us assume the what we see here, the shapes we see here, represent the workspace where the robot moves. So in the normal situation, when the robot is between point 2 and point 3 from the nearby wall, the robot would move forward. This is a normal situation. So otherwise, if the robot is beyond this range, then this PD controller would measure the error between the position of the robot and the center line, that is 0.25 from the nearby wall, and then it will, make the robot not only moving forward but also turn. So the amount of the turn depends on the error. So it turns, it gets back to the right track, to the right path, I would say. So I will get back to the code again. Yeah, please. So this is the BD controller, as you can see it. So moving forward, this method is simply saying for the robot, just go in the X direction, in the front direction. Stop means please go nowhere in X direction, or don't rotate also. So the methods that we have seen above are now all tuned and combined in one method that's called follow walls. So follow walls, it takes a state result from the action we will call it later. There is an action client, we will call an action server, so that we can get state result. We can just confirm if we have reached the starting point or not.
Right.
So we use this condition then for deciding if, okay, I have also a slide for that. It will explain it more clear. Mm, Yeah, so wall follow function. So the wall follow function takes readings from the laser sensor, and at the same time, it takes the state result. It takes an idea about the position we are in right now. So it checks whether the starting point is reached. So of course, if it is reached, then we will stop the robot and go to the next step. Otherwise, the robot would check if the front distance is less or more than 0.5. If it is less than 0.5, it means that we are nearby a corner and we have to turn. We don't have to move forward. So it goes, excuse me, there's a mouse. Yeah. So it turns. Otherwise, it comes again and make a decision also here. So it checks whether it is between 0.3 and 0.2 meter from the nearby wall. If yes, it moves forward. Otherwise, the BD controller will just correct the position. I will get back to the code again. Yeah. Sure. Yeah. So this is the wall follow function. The next function is search wall. This is a call for the surface that would find the nearby wall and then turn and then find the right direction, move forward, and so. This callback is for the distance traveled. This is a callback for the feedback from the action client. So these methods would be combined here in this function that's called Sorin. A string name, but I like it, Sorin. So Sorin combines everything together.
Okay.
Yeah. So the first thing that Sorin does, okay, I missed one point where I should also, I think, explain how the action server and the service server works. So I will start with the service server that I will call with the search, with this search function. So this is it. This is the code. But what's behind the code, I will share another slide. Okay. So this is the service server. So the service server also just subscribe to the scan, gets readings from the laser sensor, and then this makes conditions. The first condition is whether the front distance is the closest distance. If it is not the closest distance, then please rotate. And then when the front distance becomes the closest distance, please check whether the front distance is more than 0.3. If it's more than 0.3, then please move towards the wall. And after that, after just moving towards the wall a little bit, then just check whether the side distance is the closest distance. If it is not the closest distance, then the robot would turn, I would say, anti-clockwise, so that it can find its right direction for moving forward. And when it completes that, then it sends that I found the wall, and it would proceed. The robot would proceed with the next step. I will get back now to the code. Share, please. Yeah. So this is it. This is a constructor in the beginning. This is a callback for reading the laser sensor, and here is the service callback. So I call the surface firstly, and then the robot would make the first condition. The front distance compares the front distance to the closest distance, and then accordingly it would behave. If the condition is right, then it would rotate. Otherwise, it will. This piece of the code is something that I can get rid of. But I put it there because I've noticed that when the robot just rotates after finding the wall, and after comparing the front distance to the closest distance and then rotating towards the wall, so the robot sometimes does not face the wall directly. It might just be, it faces but not in 90 degree. It's not, the front wouldn't be directly facing the wall. So it will be a little bit shifted. So to solve this shift, I added more rotates. So this is the part of the code that is responsible for this. I can get rid of it, but I like using it. Okay, so then it makes sure that the robot is not in more than 0.3 meter from the wall. It moves towards the wall. I mean, then it finds the right direction by rotating, and in the end, it will send that it found the wall. So the third piece of this script is the action server. So again, I will explain the idea behind it. Yeah. So the action server, the action server gets readings
I'm sorry,
from.
Adam. The screen didn't change.
I'm sorry. Yeah.
Now.
So yeah. So yeah. So in this code, in this part of the code, the robot would get readings from the odometry sensor, and then it would check if the distance traveled is more than 7.7 meters. This condition is just to make sure that if the robot misses or passes the starting point, it will stop. After 7.7 meter, it will just send succeeded and return list of items and so on. But if we didn't miss the point, then I will publish the distance traveled, and at the same time, I will append coordinates to list of items or list of coordinates, and then checks whether the distance traveled is more than 0.3, so that I can start just checking whether I have reached the starting point or not. If I read the starting point, then it means now I have to stop, I have to send succeeded, I have to send a list of items. So how that looks like on the real code? Yeah, sure. Please. So again, this is the constructor where I define the parameters I will use. This is a callback for the odometry sensor, for the odometry readings. This is so I get the points, the X, Y, and the orientation of Z, and I put them in a point called new point, and I put a condition here. Just so on the real robot, sometimes the starting point is recorded as 0, 0, 0, which is not which is meaningless. So how to solve this is just by putting a condition. When I find that the starting point is always 0, 0, 0, 0, I will just ignore it. And I will just get the point that it would be something like 0.1, 0.2, 0.3, and so. So to avoid this 0, 0, 0 on the real robot, this does not happen on the simulation. I don't know why exactly, but this helped me in solving the problem, this part of the code. And here I'm calculating the length that's traveled, the distance that's traveled. Here the callback of the action server. So the most important part of it is this while loop that would check whether I have passed if I missed or passed the starting point with this 7.7 meter. And then it will publish the feedback, and at the same time, it will append the point to a list of points. And it will also check whether I have to travel more than 3 meters, so that I can start just also calculating the length to the starting point, so that I can say that, okay, now I'm nearby to the starting point and I can stop.
I see. Sorry to interrupt, Adam. You have 5 more minutes.
Okay. So, and in the end, if it is succeeded, it will send, succeeded, and it will send the result, which is a list of items, and it will also show the distance that's traveled. Okay, I have something else to share. Yes, yeah. Yes. Yeah. So these are the challenges I have faced. The first challenge I have faced is how to follow the walls, because in the beginning, I have tried to code the idea directly that, hey, I have to move between point 3 and point 2 to the nearby wall. And if I miss this range, please try to do it. Uh, the idea without using the BD controller was, the code was messy, was a little bit long, and the parameters were hard to tune or to find a good combination for them. And even the behavior of the robot was unexpected, to be honest. But the solution was using the BD controller, organizing the code, and also the parameters. I will talk about this point later. There are some standard methods that you can use to specify the parameters of the BD controller. So it is better than the first one. So the challenge, the last challenge, or the second challenge I found is procedural programming versus object-oriented programming. The procedural, of course, is messy, hard to debug, but the object-oriented, where I use the classes, was organized, easy to understand, easy to debug, and so the BG controller, as I have told you, that there are some standard methods that you can use, like Siglan equals, Concun, or the manual tuning. This is what I have done. Of course, there are better methods, but this is what I could have done. So I think we don't have time, no?
You have 2 more minutes.
Okay, so the manual tuning, how it works, so I have 2 parameters, KD and KP. I make KD 0 and gives a guess for the KP. And then notice the behavior of the robot, and accordingly, I will increase or decrease the KB gradually, so that I get a behavior from the robot that is smoother. It might be overshooting, but it should be smoother. To correct this overshooting of the rotation, I then gradually change the value of the KD until I reach a point where the robot would behave smoother. For future work, I think I can implement Kalman filter and use the odometry laser sensor for mapping, create a trajectory, and use a BID tuner software. So this is it all.
Awesome. Really nice job, Adam. So let me give you a round of applause here. This was really nice work, and I love that, we saw first the complete behavior, and then you've explained it so well. Do you mind? So I have a couple of comments and questions. So let me ask you. First, I wanted to say some things that I liked. First thing is the diagrams. I know it seems trivial, but it really helps us understand, and I think it's essential for good development. The diagrams you did for every situation, for the wall follower, the service server, and the action server. I thought that was really nice. Another thing that you went above and beyond that was really nice was that PD controller, and you went through all the process. This is not necessarily required, but it shows that you wanted to make a good solution, that you even went to PID, but then decided to go with the PD. So really nice there, and it showed in the smoothness of the movement. And then the last thing I want to mention that I thought was really nice, and that you mentioned that was a little strange, was that last Soreen method. I think is really great to just kind of focus your understanding on that last part, to see the whole process is really understandable, really easy to follow what the program was going to do. So that was really great. And I have just a couple of questions. Okay. So the first one is, you mentioned that you added this extra stuff in the service server, so it would be perfectly 90 degrees. Why do you think it does not do wasn't doing 90 degrees exactly, and that you had to tune that?
Okay, I think it has something to do with this value of that. So um, the robot would
Uh,
turn with this value. So
it seems
it turns.
high. Yeah, yeah.
Yeah. So if it turns too much, it misses the 90 degree. If it turns less, it
To
also misses the 90 degree. So
right.
the best thing is to correct it. So I think this is the problem. Of course, I can work on this value, change it, add it, decrease it, or so. But in the end, the solution I found was practical, to be
Yeah,
honest.
exactly.
Yeah.
Yeah, yeah. As long as it accomplishes what you need. Yeah, yeah. This might be it with the combination of how fast your node is spinning, right? The rate at which it's spinning, and then that's yeah, that would explain maybe a little bit of overshoot or undershoot of that rotation.
Yeah, yeah, absolutely right. Yeah, right. Yeah, right.
And then one more question I would like to say, and then one comment you said that was interesting. So
Mm.
um, I like that you added the 7 point, I forget, to sort of
Uh,
in case this happens. So it means you have a guardrail
yeah.
against missing that initial point. And I can see, I understand why it would miss it uh, based on these based on the state of the project, right? You can spend so much more time developing this past what we require. So my question is, how could you? Do you have any idea that how could you avoid setting this hard coded value and increase the possibility that you will not miss that initial point? Do you have
Yeah.
any clues sort of how you might go about that?
Yeah, I think there's something I can do. Increasing the length to the start point would work better.
Uh huh.
You can, for example, make the length to the start point become this radius like
A big circle, yeah.
yeah, a big circle. The bigger the circle is, the more chances you would have for stopping.
Mm-hmm. Of
So
course,
I
that
think
would
this would
mean
be,
it might not complete the full app if it's huge,
yeah,
right?
I think so. Yeah, I
Right, right,
think
right.
so. This is another problem.
Mm-hmm.
So I have no other clue, but I think maybe if you increase the length a little bit, of course, increasing it more than what's reasonable would make the robot not turning one making one loop. Until now, I have no clue, but maybe I will think about solution.
Right, yeah, yeah. So, yeah, I mentioned this because of a new addition we've done on the lab, which is, and I was thinking about this issue specifically. And if
Mm.
you notice, maybe we also have a camera topic on the robot.
Yeah.
So one thing that I think I'm going to add it to improve this project, and it's you know in the line of thinking of these improvements that
Mhm.
sometimes software can take you so far. Maybe
Mhm.
sometimes you need to add some physical things, and I was thinking, all right, maybe we can add something like a QR code that the camera can detect, right? And
Mhm.
use a fixed point of that QR code. So, but there's many ways. For example, looking at the scan um, geometry. Let's say the setup of the scan, and try to match that in addition to the odometry to sort of be able to stop, right? So there are a couple of ways, and I just wanted to mention.
It seems it sounds very interesting. It sounds very interesting.
Yeah, yeah,
Yeah.
and I will keep going into that. So yeah, I just wanted to mention that. And then one last thing that you mentioned that you didn't
Mm.
know why it happened. It says sometimes the odometry starts at 000
Yeah.
in the real robot. So that's basically, I'm pretty sure that it's because that's sometimes you try it right at the beginning of your session of your connection to the robot. And I think it's because every session we start, every time you reserve the robot and connect, we restart the robot drivers. What basically that does is just sets that odometry value back to 000. Just a nature of us restarting the robot for every student that comes along. So
Okay.
that's the
Okay, I
reason
see.
why you would see that.
Okay,
But
I
as soon
see.
as the motors start turning, then the encoders of the motors, start getting a reading, and then you'll see a different value.
Okay.
Mm-hmm.
Okay.
So I just wanted to mention that.
Thank you
Well,
for the explanation.
yeah.
Because I thought there is something wrong with the code, and I kept just for days debugging, and
Oh,
nothing.
no. So that's another thing. You kind of, in these situations when you're not experiencing, you don't have access to the robot itself or the sensors, right? You should trust the data of your sensors. Of course, that can be a faulty sensor in the robot, but there's nothing much you can do about it remotely from where you are. But yeah. So if you have a wrong sensor data, um, basically you should believe it unless you have a reason to believe why it's failing.
Okay.
So that's
This is a good tip. Thank you.
yeah. And other than that, Adam, I just want to congratulate you again. Really, really nice project. Really straightforward explanation, and it was very clear for us, the audience, to understand that. So
Thank you.
congratulations.
Thank you for hosting me. It was really interesting to present the project for you. And thank you for the tips and the ideas. There are things about the real robot I didn't think before about, but it's really interesting to talk to you.
Yeah,
I thank you.
awesome. And you'll get some of these ideas in experience with that real robot. You can start seeing that. So thank you very much. And let me just switch back here to myself. And yeah, guys, for everyone that is watching, this is what you can do when you take one of our courses that offers a certificate. You can come and present your knowledge, what you've learned in our course, and actually implement it on a real robot. And that way you showcase what you've learned, and we can be confident enough to give you that certificate of learning. So I invite everyone that is watching to do what Adam did here. And that is it for us, guys. We'll see you next time for the next presentation. And remember to keep pushing your ROS learning. Thank you, guys.